Hi, I'm Lina Roald.
And I'm Carlton Coffrin. And in this video on convex relaxations for power system optimization, we're going to introduce the basic concepts of convex relaxations for general nonlinear optimization problems to build up the basic concepts before we get into the optimal power flow problem. So the first question is this idea of a feasibility space, and what is a feasible space? And this is really a property about satisfying all the constraints in your problem. And that is basically, what variable assignments will satisfy all of the problem constraints. So let's start with a very simple example to build our intuition. Imagine you are solving a 2D problem where you have like variables x and y, and they can be anywhere in the real plane. This is, an illustration of the x and y space. And in this case, the feasibility set is every point of x and y because there's no constraints in the subject too. Now, if you come along and you tell me, okay, x should be less than 4, you can draw that as a line, like in this picture. And then if you add the less than piece, you're basically saying, okay, all the points to the left here is where the feasible space is. If you come along and say, okay, here's a new constraint, 2x plus 3y is greater than or equal to 10, you're basically adding the requirement that all the values should be less than or equal to 4 and also greater than or equal to this linear equation. So now you have this wedge-shaped feasible region. If I add one more constraint, which kind of bounds it from above, now we have a triangular shaped region. So when we say the term feasibility space, what we're really talking about is what, for some arbitrary set of constraints, which are usually inequalities, but they could also include equalities, what is the set of blue points, the assignments to the variables, which satisfy those constraints. Now, it's worth noting that this is a convex feasibility space. You can easily see that, any 2 points within the triangle can be connected with a line. But in general, the AC power flow equations are non-convex, and so the feasibility space for them could be very complicated. It could be like a non-convex shape. It could have disconnected sections. It could be really messy.
Yeah, so in order to illustrate that, let's look at a few examples. So first we will kind of look at just the feasibility region of the power flow. So like what are all the solutions to a set of power flow equations? And here is one example in a system with 2 generators that are generating certain amounts of active and reactive power. So this is an example taken from this paper, which is listed here. And you can see that this is sort of the manifold of all the power flow solutions. So as you are changing the generation at one of the generators, you will have to adjust the generation at other generators in order to kind of stay on top of this surface, which is in color here in the middle. And now what you see on the sides of this figure in black and white are essentially like the projection of this manifold, which is the surface in 3D, onto those kind of walls. So for a given value of generator 2, for example, you would see this black and white shape on the generator, like on one of the sides, and for a given value of generator 1, you would see the other donut shape in the back there, which is black and white. So this is just to give you an intuition that the power flow equations really give rise to these very complicated shapes. Another example of this of a feasibility space is shown here. So this is just to show that the feasibility space of a power flow or optimal power flow problem can be disconnected, although the problem itself is continuous. So what you see here is this kind of Nike swoosh shaped feasibility space, and the plane that is in there is really kind of a limit on the reactive power generation of the generator, which is sort of cutting off all the solutions that are below the plane. And now you see that there is this kind of part of this Nike swoosh, which is the bigger part, and then there's a small part where the green star is, which is the other part of the feasibility space. So here there's a case where the feasible space is really disconnected. So there is no connection between the blue point and the green point here. Okay, So that now that we have explained what is a feasible space, we would also like to talk about what is a relaxation, because this is of course going to be very important for our further discussion. So sort of the definition of a relaxation is that it is an extension of the feasible space. And this extension must be defined such that it contains all the feasible points. So for example, it can be like this blue shape over here. And an important part about the relaxations is that since it contains all the feasible points of the original problem, it also contains the true optimal solution to this problem. So when you use a relaxation, you are never going to cut off the true optimal solution of your original problem. So this blue shape, which is a relaxation here of the AC feasibility region, it can be non-convex. So this is what you see here. This blue shape is not convex. A relaxation can be convex but non-linear, as is the case for this yellow example. Or the relaxation can be linear. So it can be many different things. And in particular, what we are seeing here is that relaxations are really not unique. Anything that is such that it extends the feasible space and still contains all the feasible points, or is guaranteed to contain all the feasible points, will still be a relaxation of the problem. Some relaxations can be nested, so they can contain each other. So in the case of this figure, for example, the AC power flow feasibility, ACOPF feasibility region is contained within the blue region, relaxation 1, which is contained within relaxation 2, the yellow region, which is again contained within relaxation 3, which is the orange region.
And I would comment there that you can actually use that to compare relaxations to each other. So it's valid to say that R2 is a relaxation of R1, which is a relaxation of the AC. So it's like you can kind of build maybe a hierarchy of relaxations using these kinds of arguments.
Yes, good point. So in some cases, this might be possible to say that one is contained in another and, like is extending the feasible space more. But in some cases, this is not possible. They can also be complementary. So for example, in the case that is shown here now on the slide, relaxation number 2 is a relaxation of the AC power flow, AC optimal power flow feasibility region. Relaxation number 3 is also a relaxation of the feasibility region. But relaxation number 2 is not contained within relaxation number 3. So now we have talked a little bit about what is a relaxation. So it's also kind of important to talk about what is not a relaxation. So therefore we are going to compare a relaxation with kind of a general approximation. So we have this definition that a relaxation is an extension of the feasible space such that it contains all feasible points, and therefore we also know that the relaxation is going to contain the true optimal solution. An approximation, on the other hand, is an approximate representation of the feasible space. So there might be parts of the feasible space where the approximation is maybe a better sort of approximation of the true feasible space. As is here, for example, the pink region is sort of very close to the true AC feasibility region on this upper part, this kind of corner. However, with an approximation, we have the problem that it may not contain all the feasible points. So there might be feasible points that were feasible for the original AC optimal power flow or AC problem in this case, that are not feasible for the approximation. And on the other hand, the approximation may also contain points that are not feasible for the AC, the true AC problem. So, the relaxation, on the other hand, will always contain all the feasible points, but may, on the other hand, and typically does, contain points that are not feasible. Okay, so for approximations, there are two special cases. So sometimes you will hear people talk about outer approximations. So this is essentially a relaxation, because an outer approximation is kind of making sure that it is approximating the feasible region from the outside, and not cutting off any part of the feasible space. And then also an interesting particular kind of approximation is an inner approximation, what we can also call a restriction. And that is essentially an approximation which is known to not contain any infeasible points. So essentially it would be something that would only capture part of this gray region and would not contain anything outside of that gray region.
So the next question is, why do we care about convexity amongst all these different types of relaxations that we could possibly have? And the main motivation here is that convexity ensures that interior point methods and other solution methods are fast and they have guaranteed convergence properties. So if you recall, the picture on the left we've talked about in previous lectures, and it's illustrating the main issue, which is that if you start at different points inside of a non-convex region, one of these interior point methods may result in finding a local optimum solution and may not find the global optimum you're looking for. In contrast, imagine you have a convex shape like this one. What you can see here is that basically no matter where you start, you will eventually hit a frontier and then they'll all converge at the exact same point, which is right here. And this is guaranteed to be the global optimum. That's really, in some sense, the meaning of convexity, that no matter where you start, you're guaranteed to converge to the global optimum. And even better, if there's no feasible point, there's no, your constraints form an infeasible set, convex optimization will actually be able to prove that that's the case. So we tend to have a primary interest in the topic of convex nonlinear AC relaxations because they give us kind of the best combination of relaxation strength. So they're going to be kind of tight around the non-convex region, but also the performance we want from fast algorithms and the ability to, say, prove infeasibility. Now, another important concept that comes along with the idea of convex relaxation has to do with bounding the objective value. And the key idea here is that if you're minimizing your problem, a relaxation will always provide a lower bound to the objective function of your original problem. And when you're maximizing, your relaxation will always provide an upper bound to the objective function.
So, and I mean, when you say a lower bound, when minimizing, you mean that, it is you will get a lower objective value than you would if you were taking the true problem.
Right.
Or so lower or the same.
The relaxation will always kind of give you an optimistic value for what you could achieve under your original problem. Mm-hmm. So let's highlight this with an example. Let's assume our objective is trying to go up on the slide. The best possible feasible solution to the AC equations would be right here. Meanwhile, the best possible relaxation value would be right here. And you can see that the relaxation is somehow higher on the slide, so it's an optimistic value for what you could achieve. It's also worth noting that there are other AC feasible solutions, but the relaxation will always be optimistic. That's really one of the core properties of it being a relaxation. It's worth noting you can kind of formalize this for a minimization case by just observing that if you have the AC set, which is strictly smaller than the relaxation set, then the objective value, the optimal solution of the AC has to have a higher objective value than the optimal solution of the relaxation. Along these lines, there is a fairly standard metric in optimization called the optimality gap. And really what this is trying to do is measure what is the relative difference between your R star solution and some feasible solution to the original problem you had. And the standard metric is to calculate a percentage where you basically rescale, you compute the absolute difference in the objective value, and then you rescale it by your feasible solution. Just as a point of reference, most commercial solvers will set a default optimality gap of 0.01%, so that's basically 4 digits of precision, and then they say, after that, it's not really worth optimizing further. Typically, in the work that I've done, I've set the default optimality gap to be about 1% for the ACOPF problem, and that's primarily because I think we have a lot of other uncertainties about the other properties in the AC power flow. There's a lot of constants that go into setting up the optimization problem, and it's not clear we've gotten those accurate enough to really have meaningful solutions beyond 1% optimality gap.
So I have a question here. Is now you are talking about the objective value here. Can you say anything about the solution itself that you obtain?
That's a very good point. It's not clear that the optimal solution of the relaxation has anything to do with the optimal solution of the original non-convex problem. So if you look at this illustration, you can see that the optimal AC feasible solution is quite far away from the optimal relaxation point. So you would expect that the value of, say, x and y are quite a bit different in the relaxation solution than the nearest or the best feasible AC feasible solution.
So if you want to have an AC feasible solution, although you have a relaxation, I mean, even if you have a small optimality gap, you should always use the solution that you obtain from the AC feasible, from the AC optimal power flow or from the original problem if you want to have the feasible solution.
Yeah. There's no substitute for a truly feasible solution. So the next section I just want to mention about is the value of using convex relaxations for proving infeasibility. So I'll just illustrate this with a numerical example. Imagine you had a non-convex problem like this one. What is the feasible set of this particular problem? Here you can see it intersects, and there are just these two feasible points, which are right here. So this only has two feasible solutions. If I was to give you these two variants of the problem, and you can see now the parabolas are not intersecting, there's no feasible solution to these two constraints. But the challenge here is because those are non-linear, non-convex constraints, in the general case it can be very hard to prove that they have no solution. Now let's look at a simple convex relaxation of this non-convex problem. Basically what we've done is turned the equalities into inequalities, and now we've defined a feasible region, which is this kind of like ovally shape. And now we have many more solutions than just two because we relaxed it. That's what we expect. But the good thing now is if we go to that infeasible problem before and we relax it, now even though we have inequalities, there's still no feasible solution. And that's actually quite easy to prove that this set of equations has no solution. So the general argument goes, I have my non-convex equations in the bottom left. I relax them to an increased set of all possible feasible solutions, which is in the lower right. And then I use my fast algorithm to prove that that simpler problem actually has no solution. Therefore, the original, more restricted problem also has no solution. So the next general question that comes up often is, how can you improve these convex relaxations? So Line illustrated like a nesting of different relaxations. How do you go about making them tighter and tighter and tighter? One of the easiest things you can do is to intersect two different relaxations that are derived from very different equations. So just pictorially, imagine you had like relaxation 1 that kind of had this property, and then you come and you derive a very different relaxation, relaxation 2, that kind of captured the feasibility space in a very different way. And now if you intersect these two, you're going to get a tighter convex region, which is kind of represented by this greenish area, which will be a better relaxation than both of them independently.
Yeah, and I think it's here also worth noting that like when we talk about improving convex relaxation, what we really want in order to be as close as, we really want to be as close as possible, add as little as possible to this AC feasible region, right, in the middle there. So the closer we are, the closer our convex relaxations are actually approximating that region, the better relaxations we will have, right?
Yep.
The smaller, because this optimality gap that Carlton was describing before, there might be a limit to how small you can get that with a given relaxation. So as you are adding more on top of each other, you might be able to reduce the objective value of the relaxation itself to become closer to the true solution value.
Very true. The next example of improving a relaxation is the idea of adding extra constraints, which are often called valid inequalities. So the idea here is like, let's say this is your convex relaxation, and you have some intuition that there's a big section of it in the lower right, which is not very close to the real feasibility set. Maybe by doing some arithmetic math and trying a different approach to your equations, you can kind of identify that you can always draw this hyperplane from your input data, and it will cut off part of the relaxation without actually going inside the AC set. And then you can make your new relaxation, which is actually combining the original one and this valid inequality, and create this new kind of tighter relaxation. Now, both of these ideas beg the question, is there a best convex relaxation? Is there a point where we can kind of say, we're done, we figured it out, and we don't have to go any further? And this is formalized as the idea of a convex hull. So as an illustration, you can see here that basically this set R is a convex hull of this non-convex set, because if you try to tighten it into any of these kind of like little elbow shapes, you will result in a non-convex set. So there's a very important warning here, which is that if you develop convex hulls kind of independently and then you combine them in an optimization problem, that usually does not lead to a joint convex hull. So the only way to actually show that you have a convex hull is to basically consider all of your constraints simultaneously and somehow deduce, what is the tightest convex set of the intersection of all of them. And just to kind of illustrate this point, imagine I had these two very clever convex hulls of the jellyfish shape, and now I've put them on top of each other and they've intersected in a very weird way. You can see that the intersection of the blue regions is actually going to be much larger than the intersection of the gray regions, which indicates that, to define the convex hull of the intersection of the two gray regions, you would need to go back and really understand them all jointly.
So why would people want to do the convex hull separately? Is it easier than doing the full thing?
Yes. So usually it's very hard to reason about the convex hull of, say, 10 variables. People do it a lot in 2D or 3D because it's easy to visualize. 4D is when things start to get hard. And unless your problem has a very easy to understand structure, it can be really hard to generalize above 3D.
So it can really be, almost as hard to find the convex hull as trying to solve the original non-convex problem.
Absolutely. And usually, it's worth saying that usually you're trying to prove like an arithmetic form. So like I see the data and I just write, this is the convex hull of that data. And that is incredibly challenging for high dimensional information. There are other approaches, say numerical approaches, where you could try to estimate the convex hull from like sampling from your feasibility space. So there's other things you can do there, but you just need to be very careful about saying you have a convex hull, because it's quite a significant burden for a problem, a big complex optimization problem like AC power flow.
Mm-hmm.
So why are we talking about these relaxations and like all this, of solving of non-convex problems? It's because in the previous lectures we've talked about two kind of traditional approaches to solving non-convex optimization problems. One is just to solve the problem directly. The other one is to approximate it. And relaxations of the original equations is really a whole nother pillar of how you can try to address non-convexities. So if you take your original problem and you relax the non-convexities into constraints and equations, now you have numerically stable and fast algorithms. In terms of feasibility, they're rarely feasible, but the good news is that they provide this lower bound guarantee and this optimistic guarantee, which you can usually leverage in useful ways. I think the key point here is that relaxations provide a mathematical guarantee where approximations typically do not. but you could prove this for approximations as well.
Okay, so to recap this video, what we have been talking about here, so we have been talking about that relaxations of non-convex problems can lead to convex problems, which are easy to compute the solutions to. And relaxations are really useful for a number of things, and in particular, they are able to provide bounds on your objective value, and also can help you prove that an optimization problem is infeasible.
So what's coming up next is that we're going to use these intuitions we developed here, and we're going to show you how you can develop a convex relaxation of the AC optimal power flow problem. And then once we've kind of demonstrated the basics of that, we'll review tips for using and developing convex relaxations for AC power flow.